Atomic theory and measurement. Let's begin with atomic theory. Atomic theory is one of the most fundamental ideas in the whole of chemistry. It's a very old idea in terms of notions of how the world is made up. In fact, we can date it all the way back to the pre-Socratic Greeks and Democritus, and we're talking about roughly 500 years before the Christian era. But what we consider now as atomic theory really began again in the early 19th century with the work of John Dalton. As you can see, this slide is headed Dalton's Atomic Theory because Dalton gave form and shape to an atomic theory that really mattered for chemistry. Let me tell you just a little bit about John Dalton. John Dalton was born in the north of England in what is now called the Lake District in the very late 18th century. He was self-educated. That is to say, he went to school only for a very short time, but he became the protege of a very learned man who helped him gain an education. He became a teacher and taught in elementary and what we would now call middle school for many years, then moved on to work in high schools. He never became a university teacher, and he never got any further education, and he never received a further degree. In fact, he never received a formal degree of any kind. Nevertheless, through his power of mind, and in particular through his thinking about the nature of the atmosphere and the way that water vapor became introduced into the atmosphere and how it mixed with all the other constituents of the atmosphere, Dalton came up all on his own with his atomic theory and with the first table of the relative masses of different atoms. Here are the basic ideas of Dalton's atomic theory. All matter is made up of atoms. Atoms cannot be cut or subdivided. In fact, the word atom means cannot be cut in Greek. All atoms of a given element, all atoms of hydrogen, say, or all atoms of carbon, or all atoms of oxygen, are identical in their mass and in their properties, both physical and particularly chemical properties. And compounds are created by the combination of atoms in relatively small numbers. These were the ideas of Dalton's atomic theory, and they gave rise right away to a law, the law of multiple proportions. We can illustrate this law very simply. Let's suppose we have two hypothetical elements, A and B, and we find that there are several compounds that can be formed between them. Let's call those compounds in modern chemical symbolism AB, AB2, and AB3. Then you can see very directly that if we determine the masses of B that combine with a fixed mass of A, those masses will be in a simple integral relationship. 1 to 2 to 3 will be the mass of B combining with a fixed mass, the same mass of A. This is a consequence of Dalton's ideas. Well, suffice it to say that within a year of Dalton announcing his ideas about atomic theory, several other workers, and Dalton himself, had found several examples in which the law of multiple proportions applied and was quite accurate. And this gave chemists a very positive idea about Dalton's ideas and about the atomic theory. And atomic theory underlay much of what happened to chemistry in the 19th century. Now, I'd be misleading you to say it was immediately accepted by everybody. It was not. That's not the nature of scientific theories. They're not immediately accepted by all scientists. And in fact, the arguments about whether Dalton's atomic theory was actually true and whether it could be used effectively by chemists went on for at least another half century. But by the late 1900s, all chemists, all scientists accepted Dalton's atomic theory. Now let's look at current atomic theory, and in particular how it differs from Dalton's atomic theory. Can you recall the ideas of Dalton's atomic theory? Let's put one or two of them down. First, all matter is made of atoms. We have no argument with that. Second, the atom cannot be cut. Well, we don't agree with that anymore. Atoms have component parts. And you've probably heard of the names of many of these. An atom can be subdivided into simpler constituents. For example, electrons, protons, and neutrons. Later on in these lectures, we will look very specifically about our ideas about what are electrons, protons, and neutrons and how they differ from each other. But now, let's just accept that this particular portion of Dalton's atomic theory no longer holds. Secondly, all atoms of a single element are identical. Here again, we have to differ from Dalton. We now know that there can be isotopes. Again, a word you're probably familiar with. These are atoms of the same element that have different masses. Let me illustrate that with one of the most simple and striking examples. If we look at the element hydrogen, most ordinary hydrogen has a mass 1, and we will indicate that by writing it 1H, but a few tenths of a percent of hydrogen has a mass 2. We'll identify that as 2H, and this actually has a specific name. It's called deuterium. And finally, compounds are made up of the combination of different atoms in relatively simple proportions. Small numbers of atoms? Well, we now know that there are many compounds that are extraordinarily complex, with hundreds, even thousands of atoms in one molecule of a compound. The fact that we now know that many of Dalton's original ideas were not completely correct does not, however, invalidate, does not reduce the importance and the significance of Dalton's atomic theory. Dalton's atomic theory brought order to what was a very chaotic field. It led chemists to understand in much more detail exactly what was going on in chemical reactions. And as we shall see at other times in these lectures, science progresses not necessarily by the complete replacement of old ideas by new ones, but very often by the improvement of old ideas with new additions and changes. That is the way in which a great deal of new science is built upon the edifice of old science. Let's now look at the fundamental definition of an element in current chemical thinking. An element is now characterized not by a symbol, not by a mass, but by a charge, the charge on the nucleus of the element. I appreciate that I'm introducing terms that we will be explaining in more detail, but let me just outline very briefly what this implies. We now know that an element is made up of a nucleus which holds a positive charge and a number of electrons outside that nucleus, which in a neutral atom of the element exactly balance the positive charge. The size of the positive charge on the nucleus measured in fundamental atomic charge units, which we call Z, the nuclear charge, is an integer, and that integer identifies the element. If you look at your periodic table, which you can call up, you will see that each element carries an atomic number, which is simply its number in the list of elements. And that atomic number is also Z, the charge on the nucleus. It's a positive charge on the nucleus in atomic charge units. Later on, we will be examining how atoms of elements are constituted. Now, because the makeup of the nucleus of an atom can vary in the number of neutral particles present in the nucleus, called neutrons, and again we will be examining this in detail later on, it may turn out that atoms of the same element may have different masses, and those are isotopes. To be very specific in our definition, isotopes have the same Z, but different mass, which is symbolized by the letter A. Same Z, different A. What is the standard of atomic mass? Well, an arbitrary unit is defined as the standard of atomic mass. It's called, rather unimaginatively, the atomic mass unit. Shortened form AMU. And the atomic mass unit, for historical reasons and reasons of precision, which we don't need to get into, is 1/12 of the mass of one atom of one particular isotope of the element carbon, carbon 12. It is the most abundant isotope of carbon. Let's look at some atomic masses in the periodic table and then analyze them in terms of this idea of isotopes being present for quite a few elements. Here are some atomic masses as reported in an atomic mass table, and you will see that two of them, that of hydrogen and carbon, are very close to whole numbers of atomic mass units, but are not exactly whole numbers of atomic mass units. The third one, chlorine, is very different. This comes halfway between two different atomic mass units. Let's understand how this can come about by looking at the constitution of natural samples of hydrogen, carbon, and chlorine. Hydrogen first. Hydrogen is composed of two isotopes. One of them is hydrogen 1, ordinary hydrogen as it's called, and this is present to the extent of 99.98%. The other isotope, 2H, which has a special name, as we commented, deuterium, makes up the rest of ordinary hydrogen, 0.02%. And it's that 0.02% that gives hydrogen the atomic mass that is slightly different from 1.00. 1H has an atomic mass A equals 1.000 AMU. Deuterium has an atomic mass of 2.000 AMU. So that explains the slight difference from the whole number for the average atomic mass of hydrogen. And I just slipped in a word there, which is very important. The atomic masses as reported in your periodic table or a table of atomic mass are average atomic masses for the mixture of isotopes that are normally found terrestrially in the samples of those elements. Now let's look at carbon. Carbon also has two common isotopes. One of them is carbon-12. A equals 12.00 AMU, and this is present to the extent of 98.9%. The other one is carbon-13. The atomic mass of carbon-13 is 13.00 AMU, and this is present to the extent of 1.1%. And it's that 1% of the slightly heavier isotope carbon-13 that leads to carbon having an average atomic mass of 12.01. Well, you can probably guess by now what I'm going to say about chlorine. Since chlorine comes well in between two whole numbers, it must contain isotopes that have very different masses, and so it does. But chlorine, which also has two common isotopes, is made up of chlorine-35 of atomic mass 35.00 AMU, and this is present to the extent of about 75.5%. About 3/4 of chlorine is made up of this isotope. The other isotope of chlorine is not 36, but is 37 Cl. Atomic mass is 37.00 atomic mass units, and this is present as the rest of chlorine, 24.5%. Now let's do a very simple piece of arithmetic. What is the average atomic mass of chlorine made up of this mixture? The average atomic mass must equal 35 times 75.5%, that is 0.755 times 35, plus 24.5%, that's 0.245, times 37.00. And if you take the average of those two, you will find it comes out to be, I've only rounded it off to 3 digits, 35.5 AMU, which is just what you will find in your periodic table or your table of atomic masses. So an average atomic mass is what is reported for all elements in a periodic chart or in a table of atomic masses. By the way, don't go away with the idea that all elements are made up of 2 isotopes. That's by no means the case. For example, the element fluorine, which has an atomic mass of 19, is made up of 1 isotope, which is fluorine 19. Whereas the element tin is made up of half a dozen different isotopes and comes in with a very complicated average atomic mass, which you can see reported in your periodic table or in a table of atomic masses. Now let's turn our attention to measurement. Measurement is a fundamental aspect of science. The famous 19th century physicist Lord Kelvin said, if you can measure something, it's science. If you can't, it's butterfly collecting. Well, that's a little extreme, I think. There's a lot of important qualitative science, but nevertheless, the heart of a great deal of science is measurement. And most scientific experiments are carried out to measure things, to learn exactly how much of something is present in a sample, as we just saw the different proportions of isotopes in a sample of an element, or how much of a particular compound reacts with how much of another compound, and how much of a product is formed. These are the essence of scientific studies and scientific measurement, and so we must get into a discussion of measurement, of scales of measurement, of what scientific measurements mean, and how we can combine scientific measurements to get results, and what the significance of those results is. Now, the current standard for all scientific measurements is called the Système International, that's a French term, the SI in other words, and this is adopted by all scientists in every country. All scientists subscribe to the SI. The SI is based on an older system, the metric system, which has an interesting history of its own. Before the 19th century, every country had its own system of measurements, and even measurements that were given the same name in different countries had different values. For example, there was something called a foot, a pied, in France. There was something called a foot in England, but they were different. The same with the yard, etc. After the French Revolution, the revolutionary government got together a committee of very eminent scientists, including one of the greatest chemists of all time, a man called Lavoisier, and asked them to set up a system of measurements that will be independent of place or time and could be specified as fundamental for all serious measurement. And that group got together and invented the metric system, which became modified later on to become the international system, or the SI, based on the metric system. So it was that revolutionary committee in the early 19th century that actually devised the basis for what we now use as measurement systems in science. And the great chemist Lavoisier was its chair. And they invented the metric system. The story of the invention is actually quite adventurous and quite romantic, especially the story of the invention of the standard of length. It involved measuring large segments of the Earth's crust, that is around the Earth, in various different countries, and expeditions were sent out to make those measurements, and their story makes, as I said, a very romantic and adventurous tale. Well, let's look at the international system. Here are the basic units in SI. And we'll say a little bit about each of them. The units we will be using mostly in this set of lectures are units of length, units of mass, units of time, units of temperature, and a large number of units that are derived from these basic units. The unit of length was originally defined, as I mentioned, in terms of a quadrant of the Earth's crust, of the Earth's circumference. That is no longer the case. The unit of length now is specified in terms of the wavelength of a particular kind of light. You don't have to remember what that is. It's not important. Just remember that in terms of your everyday experience, a meter is a little bit longer than a yard. It's about a yard plus 3 inches, about 39 inches. We won't often use yards in this course. We will be using meters. The unit of mass is the kilogram. And you may find it a little curious that the fundamental unit of mass has a prefix which means 1,000. Kilo means 1,000, as we shall explore in a little while. Well, the kilogram is the basic unit of mass, and so far it has not been redefined in terms of anything more fundamental, although scientists are getting very close to defining it in terms of the mass of an atom of carbon. However, for the time being, when this course is being developed, the unit of mass is the mass of a chunk of platinum which is kept in Paris, and copies of it are kept in various other parts of the world, and that is the unit of mass, the kilogram. In a little while we'll see some common objects that have a mass of about a kilogram, but again, in terms of things you already know, a kilogram is a little bit more than 2 pounds. It is 10 cubed grams. Time is familiar. The unit of time in SI is the second. And the second is your everyday familiar second, the one that ticks out on the face of your watch or on your digital clock. It's defined in terms of the average time in which the Earth takes to move around the sun, and it's defined very specifically in terms of days and hours and minutes. So the units of time are quite familiar. Temperature in SI is defined in kelvins, and we will explore the relationship between kelvins and familiar temperature scales that you're familiar with, a little bit later. But kelvins are the intervals in the temperature scale on SI, and there is a 0 on that scale, which we call the absolute zero of temperature. An ordinary temperature in an ordinary room is maybe in the region of 290 kelvins. By the way, don't make the mistake of calling a temperature measurement in SI degrees Kelvin. There is no such thing. Temperature in SI is measured in kelvins. You are familiar with degrees centigrade or degrees Celsius and degrees Fahrenheit, but in SI it's not degrees, it's just kelvins. And let's look at one or two derived units. A familiar one is the liter. If you look carefully at your average milk carton, you'll see that in terms of its volume, it will be described not only in fluid ounces and quarts or pints, which is the American system, but it will also be in terms of liters. And a quart on American measurement scales is very close to a liter. It's about 0.93 of a liter. So have a look at your milk carton next time, and you will see that one that looks like this is approximately 9/10 of a liter. Now, a liter can be defined very clearly in terms of these fundamental measurements that I've mentioned above. A liter, which is a unit of volume, is 1/10 of a meter cubed. Or, to put it another way, 1 cubic decimeter. We'll look at the prefixes that are in common use in SI, but D is a prefix that means 1/10. Now it turns out that 1 liter is also exactly the same as 1,000 cubic centimeters. The relationship is such that a liter is 1,000 cubic centimeters. Putting it in terms of another unit, which is quite commonly used in chemistry, the milliliter, milli is a prefix that means 10 to the negative 3. 1 milliliter is exactly 1 cubic centimeter. And that's an equivalence we will draw on from time to time when we begin to examine the chemistry of reactions in solution, where we need to measure volumes of solutions as part of our scientific measurement. The fundamental units of the international system of SI are not always convenient for measurements, and so there are a number of prefixes applied to them which can either multiply them or divide them. And here we have the commonest multipliers and dividers. Let's show you the abbreviations for these. What the multiplier is, and an example. First one is mega. The abbreviation is a capital M. The multiplier is 1 million, 10 to the 6th. An example would be the megameter, 10 to the 6th meters. That would be a unit you might use to measure rather large distances, like the distances of the planets from the sun, something like that. Kilo, abbreviation small k, the multiplier is 10 cubed. And the example, sticking with something we know very well, is the kilometer, 10 cubed meters. A kilometer is approximately 5/8 of a mile. And next time you're in a car, have a look at the speed indicator, because you'll see it's calibrated both in miles per hour and in kilometers per hour. By the way, notice how I pronounce that? Kilometer, not kilometer. Kilometer is the correct pronunciation. And if you pronounce it that way, you'll be maybe 1 in 1,000 who do a correct pronunciation of that term. Deci is a multiplier that actually divides the basic unit by 10. The prefix is a small d, and we might use, as our example, a decigram. That is 10 to the negative 1 gram, or 0.1 grams. Centi is used particularly in length. The multiplier is 10 to the negative 2, and a familiar example is the centimeter. 10 to the minus 2 meters. Here we see a ruler reproduced both in centimeters and in inches. You notice, first of all, that the centimeters are numbered above, and that 1 inch is about 2.5 centimeters. So a centimeter is just a little bit less than a half an inch. It's a familiar measurement, a very useful measurement in many different scientific applications. Milli, prefix small m, and yes, there can be a confusion between milli and meter, and indeed you have to get used to the fact that the same symbol may be used for several different things in scientific description. The multiplier is 10 to the negative 3, and just to show you where that may come in as confusion, we'll write millimeter, mm. But that's the common abbreviation for a millimeter. It's 10 to the negative 3 meters. And you see that this centimeter rule is divided, each centimeter, into 10 millimeters. So the millimeter is a quite useful unit of measurement on the scientific scale. Micro is given a Greek letter prefix. This is pronounced mu, and is 10 to the negative 6 times the fundamental unit, the base unit. The microgram is a unit of mass used in very sensitive analytical chemistry, and is 10 to the negative 6 grams. Very small amount of mass. Nano. Now that's an abbreviation that has come into common parlance. Everybody is talking about nanoscale chemistry, nanoscale physics, nano objects. Nanotechnology has got into the language. A nano is 10 to the negative 9 times the multiplier, and a nanogram is 10 to the negative 9 grams, or 1,000th of a microgram. As we'll see later on when we explore the masses of individual atoms, a nanogram of a given amount of material still contains a lot of atoms. And finally, in this particular exploration, let's talk about pico, which is 10 to the negative 12. Again, I'll stick with units of mass. A picogram is 1,000th of a nanogram, or 10 to the negative 12 grams. And here we see a number of objects shown below, which we can describe in terms of some of these derived units, some of these multiplier prefixes along with standard units. For example, the size of an atom is of the order of nanometers. The size of a bacterium, some of the larger ones anyway, will be something of the order of micrometers. You've all seen a ladybug. It's of the order of, what, a centimeter or so in size. A mouse is quite a lot larger, perhaps a decimeter. A man, shown in this marvelous picture from Leonardo da Vinci, a man is of the order of a couple of meters in size, as is a woman, much the same. So we're here in the meter size. And then an elephant, well, we're talking about of the order of 10 meters or so in size, and many kilograms, in fact, up to the megagram in mass. So this is why we have submultiples of units and multiples of units, so that we can choose a unit that is appropriate for the object that we are looking at, the object we are describing in terms of those units. Now, I want to present to you a really fundamental idea, which is extremely profound and yet seems so obvious that you might wonder why I bother. A scientific measurement in general is a product. It's a product of a number times a unit. When I say that I am about 2 meters in height, I'm saying that my height is of the order of 2 times a meter, which I abbreviate simply to 2 meters. But don't forget the multiplier sign that really comes between these two terms of this expression. There is a multiplier in there, a times sign. Most scientific measurements are of this type. There are some that are pure numbers, but very few. Almost all are a number times a unit. And when we get into calculations of the results of combining scientific measurements, we're going to be using this, which is a very simple calculus, a very simple way of expressing a measurement, to remind ourselves that we need to include the units every time we write down, report, and calculate a measurement. Let's explore that for a moment. Let's consider the volume of a box. We'll make it a nice, simple, rectangular box. And I'm sure you recall the formula for the volume of a box, of which all the angles are right angles. This is the height, this is the breadth, this is the length, and the volume equals the length times the breadth times the height. Let's suppose we have a box of which the length is 8 centimeters, the breadth is 17 centimeters, and the height is 2 centimeters. Then the volume of the box is clearly 8 centimeters. Notice we are including the unit along with the number. 8 multiplied by centimeters times 17 centimeters times 2 centimeters. And the resultant product of those is 272 as a number. But what is the unit? It is centimeters times centimeters times centimeters, which we will express as cubic centimeters. So to report the volume of that box, I wouldn't just report the number, 272. That number is meaningless. What is the unit of the number? I would report 272 cubic centimeters, and this is a convenient way of writing cubic centimeters, centimeters to the power 3. That's a cubic centimeter. Let's do another example. Let's calculate the density of a sphere of some material. Here is a sphere, and I have its diameter which I've measured as 2 centimeters. The volume of a sphere is a moderately complex formula. Including some familiar terms like pi, the ratio of the circumference to the diameter of a circle, the diameter of the sphere, and the term 4/3. And let's say we have measured the mass of this sphere, and it equals 26 grams. Density, a very useful property, we named it when we talked about characterizing materials, and the density is one of those properties, intensive, that characterizes a material. The density, and I again apologize for using the same letter, but that's common, better get used to it, is the mass of a sphere, or the mass of any object, over its volume. So let's calculate the volume. The volume is 4/3 pi d, which is 2 centimeters, over 2, and notice I include the unit centimeters along with the 2. 4/3 pi times 2 centimeters over 2, all cubed, and that comes out to be 4.19 cubic centimeters. Again, a volume must be expressed in the cube of a length unit. A volume can be cubic millimeters, cubic picometers, cubic centimeters, cubic meters. So the density of this sphere is its mass, 26 grams, divided by 4.19 centimeters cubed. If we simply do the arithmetic on that, we get 6.21 grams per centimeter cubed. And this was really the whole object of this calculation, to stress that when I arrive at a density, I have to have a mass unit divided by a volume unit for it to make any sense at all. A density is mass over volume. The units of a density must also be mass over volume. One final example. Suppose I am looking at my average speed in a car, and I cover 72 kilometers in 1 hour, 28 minutes. The abbreviation for hour in SI is H. The abbreviation for minute is M. What is my velocity? Velocity is distance over time. My velocity is therefore 72 kilometers divided by 1 hour. And 28 minutes, let's do a little piece of arithmetic on the side, 28 minutes over 60 minutes per hour, that's an awkward number, but we'll work that out. That's 0.47 hours. So the time I've been on the road is 1.47 hours, and that works out to be 49 kilometers per hour. A familiar kind of velocity unit. You're used to talking about miles per hour in the American system. In SI, you'll be talking about kilometers per hour. And again, the unit must make sense. Since velocity is distance over time, the unit of a velocity must be a distance, in this case kilometers, divided by a time, in this case hours. This example illustrates why the atomic mass that is included in your atomic mass table, in your textbook, in your reference sources, and also in these lectures, you can pull it up at any time, why the atomic mass is sometimes a number that is very far from a whole number. And that is because many elements are mixtures of isotopes. In this case, we're looking at the specific example of copper. Look at this number, the average atomic mass of copper. It's a long way from a whole number. Now, why is that? Well, we're given the reason here. Copper contains two isotopes, one of which has a mass of 63, copper 63, and one of which has a mass of 65, copper 65. At the end of this lecture, you learned how we interpret that by means of understanding the different numbers of neutrons that may be present in the nucleus of any particular element. Elements are characterized by having the same number of protons in their nucleus, the same nuclear charge, the same atomic number, but they may have different numbers of neutrons, leading to the existence of isotopes of the element. So, 63.55 is the average atomic mass of the two isotopes of copper. Now let us suppose that copper 63 has a mass of exactly 63 AMUs per atom. And let us also suppose that it is present to the extent of X% of copper. Copper 65 has a mass of 65 AMUs per atom, exactly, and must be present to the extent of 100 minus X% of copper. That's because, let me stress this again, there are only two isotopes. If one is present to the extent of X%, the other must be present to the extent of 100 minus X% because their percentages must add up to 100%. They are the only two isotopes. So now let us calculate the average atomic mass First, let's work on the X%. We have X% over 100% of copper 63, which has a mass of 63.00 AMU, plus 100 minus X% over 100%. That's the fraction, that is copper 65, of mass 65.00 AMU. And we know what the sum of those two numbers is. Must be the average atomic mass, which is 63.55 atomic mass units. Well, let's clear that up. 0.6300x. AMUs cancel out throughout, as you can see, plus 65.00 minus 0. 0.6500x equals 63.55. Just look at that equation for a moment and check each part. We have x over 100% times 63, that means 0.63. We have 100 over 100 times 65, that is 65. And x over 100 times 65, which is 0.6500x, equals 63.55. If we simplify that, we get negative 0.0200x equals negative 1.45. And solving that for x equals 1.45 divided by 0.0200 equals 72.5. So, our answer is as follows. We have 72.5% of copper 63 and the residue 27.5% of copper 65. And that is the answer to our problem. By the way, there are only 3 significant digits that I've given in this answer, and that's because this difference is really only to 3 significant digits. Let me point out something interesting about this problem, maybe something a little unexpected. When you saw that average atomic mass of 63.55, you might well have thought that means copper must be about 50% 63 and 50% 64. But as you see, that's not the case at all. You can't jump to conclusions about the existence of particular isotopes just by looking at the average atomic mass. You have to determine which isotopes are present. And the determination of isotopes is by a technique called mass spectrometry. Which is basically making ions from the element, shooting them through magnetic and electric fields and seeing how far they are deflected. This example asks us to convert the typical mileage of an automobile, 26 miles per gallon on the highway, pretty standard for today's cars, into the average in metric units, kilometers per liter. Maybe I should tell you, you ought to get used to this, but since the United States has long since resisted the conversion to the metric system, it may be many years before you're required to know your mileage in kilometers per liter. Nevertheless, this would be the standard in, for example, most of Europe and certainly most of the rest of the world. Well, for this you need some conversion factors. And conversion factors can be calculated from first principles. We're going to cheat in this one and just go straight to conversion factors. And you can find many conversion factors listed in tables and probably in texts. I got mine from the Handbook of Chemistry and Physics. A publication that is thousands of pages thick and is published every couple of years. Brought up to date every couple of years. Now let's just look at the problem in its fundamentals. We have miles divided by gallons, we want to get kilometers, so obviously we need a factor that will give us kilometers per mile, and we want to get it per liter, so we need a factor that gives us gallons per liter. Well, we know the number here, it's 26. Kilometers per mile is 1.609. A kilometer is about 1.6 miles. A mile is about 5/8 of a kilometer. And gallons per liter, 1 gallon to every 3.79 liters. A gallon is not quite 4 liters. You may have noticed that nowadays on the bottles of liquids, milk, juice, etc., the contents are given both in ordinary American units, pints, quarts, gallons, and in liters. And if you have noticed that, then you will have noticed that a gallon is about 4 liters, a pint is about 1 liter. So, given this conversion, we can carry out the arithmetic very simply, and we get to 2 significant digits that this car that averages 26 miles per gallon averages 11 kilometers per liter. Again, only 2 significant figures are justified because 26 has only 2 significant figures, even though our conversion factors are better than that.